This is problem 13 from section B of 2014, November 2014. And when you get towards the end of the test, they start to get a little harder, to put it mildly. Well, you have a cross-section of a container shown graphically, and the sides of the container are formed by the equation y equals 0.25x squared minus 16, which is a parabola. And the first part of this, it says if the container is filled with water to a depth of h, so we don't know what that is, we'll say it's up here somewhere, the depth of h, show that the volume is given by that equation. Well, what you have, if that's a cross-section of the container, then the whole container would be that cross-section revolved around the y-axis. So this is a volume of revolution problem. So we're going to set it up thusly. So volume of revolution, we have pi out front, and the limits of integration. Well, we want to slice it perpendicular to that axis, which is this direction. So up and down, that is dy. So everything has to be in terms of y. So you're going to slide that thin cylindrical disc from the bottom, which is 0, up to the unknown height of h. And now all we need in the inside of this is the radius squared. So this is the radius squared, and then dy. So the radius has to be in terms of y. Well, we're given the equation. The radius is the distance from here to there, and that distance is x. So the radius squared is x squared. There's the radius squared. But we can't put that into the integral since everything's in terms of y. So we take the equation given y equals 0.25x squared minus 16 and solve that for x squared. So add 16 to both sides. Y plus 16 equals 0.25x squared. And multiply both sides by 4. Because 0.25 is a fourth. That'll get rid of that decimal. So we have 4y plus 64. Except I'm not going to distribute it because I'm looking at their answer. So it's 4 times y plus 16 on both sides. Now that is equal to x squared. So that's what goes into the integral. We put 4 y plus 16. And that's the radius squared. So let me take this out of here now since we don't need that anymore. If it'll go away. There we go. Alright, so the only thing left to do here is to integrate this. I can kick the 4 out front, so I got 4 pi. The integral from 0 to h of y plus 16. Which is pretty easy. So 4 pi is still kicked out front. Parentheses, increase y squared over 2 plus 16y. And we need to evaluate that from h down to 0. Well, if you put a 0 in there, you're going to get 0. So all we have to worry about is the h. So 4 pi. Put h in for y. We have h squared over 2. And then 16 times y would be 16h. And presto, there's what we wanted. So that is the volume of revolution. So that indicates the volume of the container for part A. Kind of a hard 3 marks. In part B, we're told that water is starting to leak out according to this formula. Circle the wrong one in the directions. So dV dt is negative 250 square root of h over pi times quantity pi, h plus 16. And we're supposed to show what dH dt is. Now, dH dt, we need an equation in terms of h. So the volume from the first part is given up here in the corner. And then what we're going to do, we know we're going to take the derivative of both sides of this equation. So dV dt, because we want to do it with respect to t. I think what I'll do, I'm going to distribute this first. So the 2 cancel, so I got 2 pi h squared. Now this is not the derivative yet. I'm just going to distribute. And then 64 pi h. All right, now I'll take the derivative. So I've got 4 pi h plus 64 pi. And that's all dH dt. Okay, well, I'm trying to find what dH dt is, so I've got dH dt. Now, the change in the volume on the left-hand side was given. So I just fill that in. That's 250 square roots of h over that denominator given. And this is negative because the water's leaking out. Close that. So that's equal to 4 pi h plus 64 pi dh dt. So I'm going to divide both sides by 4 pi h plus 64 pi, and this is going to get a little messy. I can see it already. So that's the numerator, and on the denominator I'm going to go ahead and distribute that as pi h plus 16 pi. Now I'm dividing by 4 pi h, so I put that on the denominator, so 4 pi h plus 64 pi, and that's going to equal my dh dt. Well, we've got dh dt, we just have to make it look like theirs. The numerator's done. Now, how can we make the denominator look like that? Well, I think what I'll do, I'll just FOIL out that denominator. So first times first is 4 pi squared h squared. The outers is going to be 64 pi squared h. The inners is going to be 64 pi squared h. And last times last is 16 times 64 pi squared. Let's see, 16 times 64, I gotta grab my calculator here. 1024. Okay, so that, what I just wrote out is the denominator. Let me scroll up and get a little more room here. Yeah, clean up that denominator because I'm trying to get it to look like what they're telling us to show. What can I do here? Let me combine those terms together. 4 pi squared h squared plus 128 pi squared h plus 1024 pi squared. And why don't I factor out some stuff here, like a 4 and a pi squared? If I take out the 4 pi squared, now it's starting to look like theirs. Now this is all the denominator I'm just working with right now. So what's left is h squared. 4 into 128 goes 32h. And 4 into 1024 goes 256. And I think, yep, that's going to factor in. It's a perfect square trinomial, so it's 4 pi squared, which is out front, h plus 16 times h plus 16, which is h plus 16 squared. So I've got it. Now if I can just put it together, draw an arrow here. So dh dt equals negative 250 square roots of pi, h rather, over what I just found to be the denominator, 4 pi squared, h plus 16 squared, quantity equals dh dt. So that was kind of complicated, but that is the end of part Roman numeral 1. For part 2 of B, state dt dh and show that t equals, well, we just did dh dt, so dt dh is just the reciprocal of that. So let's just take that previous answer, dt dh, and flip it. So that's 4 pi squared, h plus 16 squared. I'm going to go ahead and multiply that out, go back to where we were, 32h plus 256. And that is all over 250 square root of h, which I'm going to write as h to the 1/2. And this is negative. Okay, at this point, I'm trying to solve, if you look at the problem, I'm trying to solve for t. So in other words, what I want to do is separate the variables. So dt stays on the left. I'm going to multiply both sides by dh. And I'm also, I'm looking at their answer. No, they kick out the, okay, I was thinking about distributing on the numerator, which I'm not going to do because I can see they've kicked that out. So, multiply both sides by dh. And I've got negative 4 pi squared over 250. I'm just going to go ahead and separate that. And then h squared times h squared plus 32h plus 256 all over h to the 1/2. and that is I multiply both sides by dH. All right, so if I'm trying to solve for t, well, all I have to do is integrate both sides because I've separated the variables. If I integrate dt, I'm going to get t. If I integrate the right-hand side, I'm going to take a big integral, stick it in front, but I'm going to kick out that constant factor, negative 4 pi squared over 250 times the integral of h squared plus 32h plus 256. I guess I'll go ahead and write it. It's just time consuming, but I better not skip any steps. Over h to the 1/2, and then they don't want you to actually integrate this, which is nice. They just want you to make it look like their answer. Well, that's easy enough because we can use our exponential properties. H to the 2 over h to the 1/2. You subtract the powers. So we're done. Keep that constant out front. And times the integral of h to the 3/2 plus 32h to the subtract the powers 1/2 plus 256. Oh, I forgot an h somewhere. Where the h did my h go? No, I didn't. I guess that, oh, I was just not reading that right. That's I was going to say, that doesn't make sense. I thought that was 256h to the 1/2. It was 256h to the -1/2, which makes sense because that h to the 1/2 is in the denominator. There we go. Everything's fine. And it's done, and it's beautiful. Okay, so what we're going to do is use the answer from part 2 to answer part 3. Find, correct to the nearest minute, the time taken for the container to become empty. Well, for it to become empty, we'll have to have a volume of 0, or a height of 0. The height of the container will be 0, and then it's empty. So I'm going to take this integral that we got from part 2, negative 4 pi squared over 250, and I'm going to integrate it from, I want it to end at 0, so I put a 0 on the top, and if you remember, the initial height was 48. So we're going to integrate it from 48 to 0, and then this integral. Now you could do this by hand. You don't have to, since this is on the calculator section. As long as you set up your integral and show what you're doing, you're going to get full credit. What they're looking for, can't forget my h, plus 256. Sorry, it's getting a little crowded here. H to the negative 1/2 dh. Squeeze it in. There we go. So there's our integral, and we're going to integrate from 48 to 0. And you can, since this is on the calculator section, use your calculator to evaluate that integral. So this is equal to t. As I said, you don't have to do the actual integration. So t is going to equal, if you punch that into your calculator, you get 2,688.756. And that, remember, up here it told us the time was measured in seconds. So that's seconds, but the question here is asking for minutes. So you just take this, divide by 60, and it says the nearest minute, I believe. Yeah, the nearest minute. So you just round it off to the nearest minute, and it turns out to be 45 minutes. So that was a lot of stuff in Part B for those 10 marks. Well, that wasn't just Part B, rather. Let's see. 10 marks was for the whole thing, I think. No, that was Part B, 10 marks. Okay, we're good. And we just have one little part left. See if I can scroll up and grab that without pausing, because I think it's pretty quick if I remember right. Here it comes. Okay, once the container is empty, water is pumped back into the container at a certain rate, 8.5 cubic centimeters per second. At the same time, water continues to leak out at that same rate. Use an appropriate sketch graph, determine the depth at which the water ultimately stabilizes. Well, you can do this. Well, we know, let's set up a rate here. The change in the volume. Okay, the water is being pumped in at 8.5. So it's 8.5. That's the rate at which cubic centimeters per second. The rate at which the water's going into the container, but we're going to subtract out the rate at which it's leaking out, which is that 250 square root of h over pi plus times h plus 16. Okay, so that's the change in volume rate. That's how fast the water is changing. And we're trying to find out when it stabilizes. So in other words, it's going to reach a point at a certain height, since the container is kind of flares out. It's going to reach a point at a certain height where the water that's going in and the water that's flowing out, they're kind of neutralize each other. So in other words, we want to check this or set this equal to 0. So using an appropriate sketch graph, what you can do is just graph this. I'm not going to do it because all you have to do is punch this in. Go to y equals, punch that in, replace your h with x, and see where that equals 0. And just find that root. So we're trying to find when the change in the volume is 0, stabilizes. And if you do that, graph it, it turns out that h is about 5.06 centimeters. Okay, that is the end of problem 13. As I said, 13, those last problems are always the toughest problems. They take the longest. But just plow through it. Get as many marks as you can, as I always say. You're not going to get every mark, but that's okay. As long as you get some, and you all do great. All right.